Hello class, welcome to this video, the fourth video in the Calculus 1 series. So we're going to continue our discussion of limits. Here we're going to focus on continuity and one-sided limits. So we're going to go ahead and discuss continuity on a point/open interval. So a function that is continuous, so when we think of continuous, we think of functions that have no holes, jumps, or asymptotes. So this is generally what we think of. We think of continuity as if you were to trace the function with a pen or pencil from left to right, are you going to have to lift your pencil in order to, trace the entire function? So in this case, if I were to do this part right here, well, I would have to lift my pen in order to plot this and then continue with the rest of the graph. So it's sort of like an informal way of thinking about it. So in the same way, we have holes, jumps, or asymptotes. There are different types of discontinuities. So there's removable and non-removable discontinuities. So this first one here is a removable discontinuity, and we'll talk about what that means later. This other one is a jump discontinuity because I have to jump from one curve to the other in order to continue the graph. And then we have another removable discontinuity. It's a hole, right? But a hole is considered a removable discontinuity. And then you have an infinite discontinuity because this graph is approaching this asymptote, and this is the asymptote right here, this line, this dashed line that you see. And so these are all considered discontinuities, right? So let's go ahead and define continuity at a point. There's also another type of continuity that we'll discuss in a little bit, besides these ones that we just mentioned. But let's go ahead and define continuity. First off, the function has to be defined at x equals c. So if you're doing the continuity at a point x equals c, right? At x equals c, for example, that's at a point. Then f of c has to be defined, right? Meaning it can't be a hole. And then number two, the limit has to exist. The limit of the function as x approaches that value c has to exist. If it doesn't exist, that means that it's not continuous at that point. In addition, the final condition is that the value of the limit has to equal to the value of the function at c. So not only do the function has to be defined and the limit has to exist, they have to be equal to each other. So if we want to define continuity on an open interval as opposed to a point, so in this case an open interval between two numbers a and b, then for it to have continuity on the interval, it has to be continuous on every single point in that interval. Okay, so this could be a value c in between a and b, or any number between a and b. All those numbers have to be continuous, right? Using the top three conditions in order to have continuity at each point in the interval, for it to be continuous on the entire interval. A function is continuous everywhere from negative infinity to infinity if it is continuous for all real numbers, right? For all x in the entire number line. Okay, so let's take a look at different continuities here. So a discontinuity is removable if we can eliminate it by redefining the function at that point. And in a discontinuity is non-removable if we cannot do that. So if we can't just simply eliminate it by redefining the function at that point. So for example, if I were to look at this portion right here, because that is removable, because if this is the function f of x, right? Well, clearly we know that f, let's call this f at c, is undefined, right? However, if we redefine it so that we can say that this point is actually equal to that, so for example, we could say that f of c is equal to 2 because this is the value 2. And then we can end up filling this hole here. So instead of having this point being at 3, we can have this point being at 2 and define it. So we could write it as a piecewise function, saying that this is equal to some function when x is not equal to 2, but it's equal to 2 when x is equal to 2. this blank here is this function right here, this triangular looking function. So whatever that function is, we can define it to be that function as long as x is not 2, but then define this to be 2 in order to fill in that gap. So hopefully that kind of makes sense. But we can, so in other words, we could just redefine the function and fill in that hole or fill in that gap. So that's removable discontinuity versus non-removable. And in this example, jump and infinite discontinuities count as non-removable because we can't simply just define it in order to remove it. So that's something to keep in mind. Another discontinuity that I promised I'd mention is the oscillating discontinuity. This is the other one that I mentioned earlier that we were going to talk about, this type of discontinuity. But this is an oscillating discontinuity, and it's non-removable. And we actually looked at this at a previous lesson. If we looked at sine of 1 over x, if we look at x equals 0, we can see that it's oscillating and doesn't approach a single value at 0. So this is what we mean by oscillating discontinuity. Now this is bounded. This is called a bounded discontinuity because notice that it has upper and lower bounds. So it has -1 as a lower bound and it has +1 as an upper bound. So it clearly has bounds for the oscillating pattern. However, infinite discontinuities are unbounded because there is no upper or lower boundary. It just continues on without bounds. Okay, so there's a few definitions, a few vocab terms here as it relates to continuities, or discontinuities rather. So let's look at an example. Actually, example 1, but with 3 different examples within it. So we want to determine whether they have removable or non-removable discontinuities. So looking at the first one, -4 over x minus 2, we can see that there's an issue with the value x equals 2, right? So if we look at it, it has an infinite discontinuity at x equals 2. Infinite discontinuities, you can tell that they're there because you cannot divide by 0. So if you have something where you're dividing by 0, that's automatically going to be an asymptote, right? A vertical asymptote, which is an infinite discontinuity, okay? Those are things you want to look out for. So it is non-removable since I can't eliminate dividing by 0, right? That issue with dividing by 0 by redefining f of 2 to make it continuous. Okay, so this is an infinite discontinuity. Let's show you the graph. So this is how the graph looks like. So if you're to graph it, it's a hyperbola, and we know that there's a vertical asymptote right here, VA, at x equals 2, which can't be simply removed by redefining the function at the points x equals 2. Okay. All right, so if I look at the next example, we can see that there's also an issue with the value x equals 2. However, this is a removable discontinuity because I can actually cancel out that 2 if I look at the function. So we're going to say first off it's discontinuous at x equals 2, but it's removable because we can actually redefine it. So we'll show you that right now. So if I look at the function, I can factor the numerator using the difference of squares, and notice that these cancel oops, no, I canceled out the wrong ones. So these are the ones that cancels, so leaving me with x plus 2. But notice that this function is only defined for x not equal to 2, right? So what we can do is we can actually remove that hole by defining the function at x equals 2. So we can redefine g of 2 as g of 2 equals 4. And the reason why we use 4 is that if we were to plug in 2 in here, we would get 4, right? So if I defined it, then we can remove the discontinuity. So in other words, if I defined g of x as the piecewise function given by x squared minus 4 over x minus 2 when x is not equal to 2, and then I can define it as 4 when x is equal to 2, well then I'm able to eliminate the hole. If you see the graph here, you can see the hole at x equals 2 when the y value is 4. See this hole right here? So this is the function g of x, and it's clearly a hole, so it's a discontinuity. However, it's removable because if I define it in this way, I can actually fill in that gap if I wanted to. Okay, this is why we refer to it as removable. Okay. All right, so if I look at the third sub-example, for example 1, we have a piecewise function. Is it continuous? Well, the answer is, well, we have to look to see if the hole is filled. We know that this was the function we looked at earlier, and there was a hole at x equals 2, right? So this actually is continuous everywhere because normally it would have a discontinuity at x equals 2. However, that was removed by redefining h of 2 as 4. So if you look at it, if we look at the example, this is what we did earlier. We canceled these out, right, and gave us x plus 2. That was valid when x was not equal to 2. In this example, they're saying that we want it to be less than 2. However, if I do h of 2, right, if I were to do h of 2 here, then that would give me 2 squared, which is 4. And we know that since this could be 4, when I do 2 plus 2, that gives me 4. These values both agree. That means we have a hole that is filled, okay? So since the hole at x equals 2 is filled, it was removed by redefining h of 2 as 4, then there are no discontinuities. Okay, so this was the hole that was there before, right, when x is 2. However, it was filled by this orange function because we know that 2 squared is 4, and so it happens to be here, and so it fills in the gap that was initially left by the blue function. And therefore, this whole thing is entirely continuous. So it's continuous for all real numbers, for all numbers on the number line here. And so there are no discontinuities. All right, so we have we're going to take a look at the concept of one-sided limits. So far, the limits discussed in this course have been two-sided limits. So for example, the limit of f of x as x approaches c is equal to L. That actually implies two one-sided limits. It actually implies that the limit of f of x as x approaches c from the left side is equal to L, and the limit of f of x as x approaches c from the right side is equal to L. So when we say general limits, we actually mean these two one-sided limits. So these are the limits from the left and from the right, respectively. So it's read as the limit of f of x as x approaches c from whatever direction you want, left or right. So looking at the graph that we looked at, that we examined in example 1, using that same graph, if I were to do the limit as x approaches 2, remember this value is 2, if x approaches 2 from the left side here, so if we were to draw those arrows, this is the value 2 here, and so it's approaching 2 from the left side. So as x approaches 2 from the left side, well, the graph, we're basically just traversing the graph here, right, from the left. And as we traverse the graph from the left, it's approaching this value of 4, right? Now, if we approach it from the right side, from approach 2 from the right, well, then that's these two arrows. We're basically traversing this graph from that side. It still approaches the value of 4, right? So the one-sided limits are both 4, which means that because they're both 4, that means they agree. If those two one-sided limits agree, then that means the general two-sided limit, the limit of f of x as x approaches 2, that exists, and it has to be equal to 4. All right, so we know clearly that the limit is 4, but we're just demonstrating that the two one-sided limits must agree and also equal to 4. So, so just a couple of tips here, a couple of things to keep in mind. If the two one-sided limits both exist and they agree at a specific value, in this case L, let's say they both agree at the value L, then that means that the two-sided limit must exist and that limit must be equal to L. Okay, so in other words, if you have two one-sided limits that are equal to each other and they're equal to each other, the same number, then the general limit must exist and must be equal to L. Now, on the other hand, if either of the limits do not exist or does not exist, or they're not equal to each other, then the limit cannot exist. The two-sided limit cannot exist. All right, so this is actually theorem 4.1, the existence of a limit. So let f be a function and let c and L be real numbers, be an element of the set of real numbers. Then the limit of f of x as x approaches c is equal to L if and only if, right? So this is if and only if if and only if the limit of f of x as x approaches c from the left is equal to L, and the same limit but from the right side is equal to L as well. So they both have to be equal to L, they both have to agree in order for the limit to exist. This is what we were talking about earlier, okay? All right, and we're going to actually show a picture of that. So for example, if I have a graph like this, right, where we can see, and let's say we have this point right here. Well, we can see that let me change the graph a little bit. So let's say we have something like this, right? And let's say this is on the real number line. This is 5 and this is 1. So we can see from this function that this should be here. Sorry. We can see from this function, this graph, that if this, let's say this is c, right? Well, then if I were to do the limit as x approaches c from the left side, well, that's going to be equal to the value of 1, because as I approach c from the left side, I'm actually traversing this portion of the graph, right? And that's the value of 1. And if I were to do the limit as x approaches c from the right side, well, then that would be traversing in this portion of the graph, which is a value of 5. So we can see that the two one-sided limits do not agree, and therefore the general limit as x approaches c from either side does not exist. Okay, so this is what we're mentioning. All right, so let's look at an example. So find the limit of f of x equals negative square root of 9 minus x squared as x approaches negative 3 from the right. So basically we're doing this limit right here. This plus indicates that we're doing the limit from the right side. Okay, so we're doing that limit. Now, when you do one-sided limits, you basically approach them the same way that you would do a two-sided limit, a general limit. You can do a direct substitution, and if direct substitution doesn't work, of course you can you can manipulate the function or whatever in order to get a limit, or it just may not exist, right? So here we're going to try to direct substitution and try to plug it in. Now, if we plug that in, well, we're going to show you this graph. This is the graph. This graph is a graph of a semicircle, and it's negative, so that means it's downward. If this were positive, the function would be going like this, right? It would be an upper semicircle. But it's negative, so it's a downward semicircle. And if you want to remember that, well, if you want to remember that, then or like know why that is, well, if I were to square this function, I would get y squared equals 9 minus x squared. And if I move the x squared over to the other side, I get x squared plus y squared equals 9. So this is the equation of a circle, right, with a radius of 3. So this is actually a radius of 3 for the circle. But since we're taking the negative square root, that means it's a downward semicircle, okay? So that's the reason why that's the case. Just as a refresher, just in case you needed that refresher. But in any case, if we approach from the left side, right, using these arrows, then we can clearly see that it's approaching this value of 0, right? That's a value of 0 on the y-axis. So this is actually equal to 0. Okay, so that's based off of the graph. However, if you were to do direct substitution and you were to just plug it in, then you would get the same answer. You would get 0. Okay, because negative 3 squared is 9, and then 9 minus 9 is 0. Okay, so you get the same answer if you do the graph or direct substitution. All right. Okay, so we're going to look at some new types of functions. You may or may not have seen these functions before, but we're going to introduce them to you. These are known as the floor and ceiling step functions. So the first one we're going to illustrate is the greatest integer function, also known as the floor function. These belong to a class of functions known as step functions. Here are some examples of step functions. You can see they're step functions because they resemble steps. Now you see these dashed lines here, they may or may not be on the actual graph. So you may not have those dashes there. It may just be this, that, right? So it may just be, they may not have these dashed lines on there, but they show that dashed line so you can kind of see it kind of resembles a step. But these are step functions, and we're going to focus specifically on the floor and ceiling step functions. Let's start with the greatest integer function, also known as the floor function. The symbol for the greatest integer or floor function are these two. This is generally the one that we'll use. However, this notation is good because you can see that this bottom part is on the floor, and that's how you can remember that that's a floor function. The floor function of x is equal to the greatest integer n, such that n is less than or equal to x. So in other words, in order to evaluate the floor function at x, you basically have to come up with an integer that's the biggest integer that is less than x or equal to x. So for example, if I'm evaluating the floor function at 5.9, well, that's going to be equal to 5, since 5 is the biggest integer that is less than 5.9 or equal to 5.9. And that's the floor function. And then if you're looking at negatives, don't be confused, because remember, when you're at negatives, the greater the absolute value of the negative number, the smaller it is, right? So if I'm doing the floor function at negative 3.1, well, that's going to be negative 4, since negative 4 is less than negative 3.1 or equal to it. Okay. All right. So there's also the other side to it, which is the ceiling function, which has this line on the upper part, like the ceiling, right? So it's easy to remember. But this is the smallest integer that is greater than the x. Okay, so for example, the ceiling function at 5.9 is equal to 6, and 6 is the smallest integer that is greater than 5.9 or equal to it. Similarly, the ceiling function at negative 3.1 is negative 3, since negative 3 is the smallest integer that is greater than negative 3.1 or equal to it. All right, so we're going to focus on graphing the greatest integer function and show you how it looks like. So we're going to come up with some values for x. So we got negative 2, negative 1.2, all the way to 2.8. And we're going to evaluate the step function at those values of x. So if I were to do x equals negative 2, well, that's obviously going to be negative 2, since negative 2 is less than or equal to negative 2. Now, if I were to do negative 1.2, the value is going to be negative 2, because negative 2 is less than or equal to negative 1.2. Okay? It's got to be the greatest number that is less than the number inside the brackets. And then if I were to do negative 1, well, then obviously it's going to be negative 1, because negative 1 is less than or equal to negative 1. Notice that if I were to continue this is going to be a line, because we have all these points in between, and this is going to be a hole here, because we can't have negative 2 as a solution when x is negative 1, because we just said that we get negative 1 for the answer. So there's a hole there. Okay. If we were to do negative 0.2, that's going to be negative 1. If we were to do 0, then that's going to be at 0, and therefore there's a hole here, and then this is a line that continues. If we do 0.8, we get 0, because 0 is less than 0.8. If we do 1, we get a value of 1, because 1 is less than or equal to 1. And then therefore we got a hole there, and we're going to continue this. If we continue this, we get the step function given. Okay, so that's how it looks like. I'm going to show you how it looks like in a better format here. So here we go. That's the step function, the greatest integer function, otherwise known as the floor function. Notice that we didn't really do the little dashes here, right? It's just completely flat. It's just a bunch of flat lines here. All right, so we're going to compare the floor and the ceiling functions, so you can see the difference between them side by side. So if I juxtapose the two, you can see that not only are the values for the steps different, the holes are actually placed in different locations, right? You can see the holes here are placed first rather than last. Okay. All right, so example 3. Let's look at the greatest integer function and evaluate the limit as x approaches 1 from the left and 1 from the right. So if I do 1 from the left, let's look at some numbers. If I plug in 0.5 versus 0.99. If I plug in 0.5, notice that I'm doing this because I'm approaching 1 from the left side, right? But they're both going to be 0 because these numbers are less, or because 0 is less than or equal to 0.5 and 0 is less than or equal to 0.99, right? So it's going to be 0. So we know the left side limit is 0. Now let's do the right side limit. So here we're approaching 1 from the right side. So this is 1, but we're approaching it from the right, from the right side, right? So then if I do 1.5 and 1.01, they're both going to be equal to 1 because 1 is less than or equal to 1.5 and 1 is less than or equal to 1.01. So the one-sided limit is 1. Okay, so since the one-sided limits do not agree, that means the limit does not exist. So those limits do not exist. Or the one-sided limits are not equal, and that implies the limit does not exist. Here's a graph of this so you can kind of remember how the step function looked like, the greatest integer function. So if we approach from the left side of 1, this is the value 1 right here. If we approach from the left side, we get a value of 0. If we approach from the right side, we get a value of the right side of 1, then we get a value of 1. Okay? All right, so now we're going to use the idea of one-sided limits in order to define what it means to be continuous on a closed interval. All right, so now we can officially define continuity here on a closed interval using one-sided limits. Okay, so a function has to be continuous on the closed interval b, where we're including ab, if it is continuous on the open interval ab, and so not only does it have to be continuous on the open interval, meaning it has to satisfy those 3 properties, meaning that the limit exists, the function at that value exists, and they're equal to each other, but it also has to have the following 2 one-sided limits. Okay, so the limit as x approaches a from the right must equal to f of a. The limit as x approaches b from the left must equal to the function at b. Okay, and that's what makes these closed. So in other words, if I approach a from the right side, if I approach a from the right side, that limit must equal to the function at that point, right? If I approach b from the left side, then that limit must equal the value of the function at that point. That's basically what it's saying. And if that's true, then that means there's no holes on a or b, and they're completely filled. That's what it means to define continuity on a closed interval. Now there's different combinations that you can do. So you could do continuity on the mixed interval AB where you include B, or AB where you include A and not B. So let's look at the first or the second example where you have a mixed interval. So the function f is continuous on AB, include A inclusive, B exclusive, so you're excluding B. If it is continuous on the open interval AB and has the one-sided limit as x approaches a from the right, and that's equal to f of a. Okay, so this is a picture of that. So here we can see there's a hole here, meaning it's not including b, right? That's why there's a parentheses there, and there's a bracket here, which means we're including a. So a is included in the continuity, and there's clearly not a hole there. It's completely filled. And we know that that's the case because if we take the limit as x approaches a from the right side, then we can see that it actually agrees with the value f of a. Okay, and therefore it's closed there. Now if we do the limit of b as we approach it from the left side, we can see that we have a limit there, but it does not agree with the value of the function because there's a hole there. Okay. So if f is continuous on the mixed interval AB, where it's b inclusive, right? So it's including b but not a, then it has to be continuous on the open interval AB and has to have the one-sided limit from the left side of b, and that has to agree with f of b. So here, this is sort of like the opposite, right? Here, there's a hole here, so that means that there's a parentheses at a. Here B has the bracket because it's completely filled. There's no hole there. And we can see that if we take the limit as x approaches b from the left side, then it's going to agree with the value of f of b. Okay. All right, so we can also do other combinations. So for example, negative infinity to b, or a to positive infinity, for example. So we're going to look at those examples as well. So let's say we have negative infinity to b inclusive. So we're including b. So it's continuous on that interval. If it is continuous on an open interval, negative infinity to b, and it has the one-sided limit, x approaches b from the left, and that agrees with f of b. So here's an example of that. Notice that this continues without bound. It continues without bound as x goes to negative infinity, right? As x goes to negative infinity, this continues going in some direction. It doesn't really matter if it goes up or down. We know it's continuous because it's smooth, right? No holes or anything like that. Now, if this is not a hole, it's filled, because as x approaches b from the left side, we can see that it agrees with that value, which is filled. Okay. And then on the other hand, we could do it's continuous from a to infinity, including a. If it is continuous on the open interval a to infinity and has the one-side limit, so if we approach it from the right side, then it must agree with f of a. However, for b, it goes on forever, right? So there actually is no b here, so we can get rid of that. So I'm going to get rid of that b, because I mean there is a value b. However, it's not bounded. It goes beyond b, right? It goes to infinity. It continues. All right. Okay, so let's look at an example. Discuss the continuity of f of x equals square root of 2 minus x squared. So if I look at this function, we know that the domain has to be negative square root of 2 and positive square root of 2. And the reason is that if I were, again, like we said in the other example, this is actually the equation x squared plus y squared equals 2, which is the equation of a circle. So this graph is actually the graph of a semicircle that is going up, because this is a positive square root. And the reason why we know is that the equation of a circle is x squared plus y squared equals r squared. And so therefore r squared must be equal to 2, and so r has to be square root of 2. So that means that these here are square root of 2 and negative square root of 2. And this is a circle at the origin. So let me erase this real quick. So if I were to solve this, right, I can just subtract x squared on both sides. And then I take the square root. But when I take the square root, I usually do the two-sided square root, right, where it's plus or minus. However, the function is plus, so therefore we just have the plus version of it. So it's a graph that's just going up, right? It's not the negative version. Unless we did plus or minus, that would include both versions, but we do not have plus or minus. We just have the plus version. So just a quick review of that in case you weren't aware. But that's how the graph looks like, and that is why it is the way it is. So the domain, so clearly the domain is from negative square root of 2 to square root of 2, including those two numbers. So f has to be continuous on all points in the open interval because it's a semicircle. Semicircle is continuous on all points, right? There's no holes on that semicircle. Now we can take the limit. We're gonna see, so we know right now that we have this. However, we want to see, is this closed or not? So we want to see if that's a closed interval. We know that it is because based off of the graph, right? However, let's do the one-sided interval or one-sided limits. So if I do it in the square root of, or negative square root of 2 from the right side, I could just do a direct substitution and that gets me 0, right? So if I do square root of 2 minus negative square root of 2 squared, that's going to give me square root of 2 minus 2, which is 0. But notice that this is the same thing as f of negative square root of 2. So if I plug in negative square root of 2 here, I get the same result. So therefore it is closed at negative square root of 2. If I were to do the square root of the limit as x approaches square root of 2 from the left, again, I can just do a direct substitution and I get 0, which is the same result that I would get if I plugged in square root of 2 into the function. And therefore we can conclude, this symbol right here means therefore. So sometimes you'll see me use that. So therefore, we can conclude that f is continuous on the closed interval, all right? So basically look at the limits to see if you get the same value as if you would if you just substitute, plugged in, evaluated the function at that value when we do the one-sided limits. And this is how the graph looks like. This is what I was mentioning earlier. And this is negative square root of 2 and this is positive square root of 2, and it's clearly closed on that interval, and it's continuous. All right, so knowing the graphs really helps out with these, like knowing basic algebra and like what the functions look like. Having good knowledge of graphs is very essential to some of this, or at least at the very least know how to do it using technology in order to come up with your conclusions. All right, so let's look at theorem 4.2. So properties of continuity. So if you have a number k, which is a real number, and f and g are continuous at x equals c, then it must follow that the given would also be continuous. So if I have the function f and I multiply it by a scalar, remember a scalar is like a constant, right? So k is a constant, k is a real number. So if I multiply the function by k, then that function must also be continuous at x equals c. So for example, tangent x is continuous at every point in its domain, right? When I mean every point in its domain, I mean the domain of tangent. We know the domain of tangent. We know that tangent looks like this, right? And it has asymptotes at pi over 2, negative pi over 2, and so on and so forth, right? But we're looking at within its domain. So within its domain, it is continuous. Like basically between the asymptotes, we know it's continuous. If that's true, then that means if I multiply tan by 3, that must also be continuous, okay? All right, so now let's look at the sum or difference. If I take two functions, f and g, and they're both continuous at c, then the sum or difference must also be continuous. So if I have x squared as a function and square root of x as a function, we know those are continuous everywhere. So if I add them together, that must also be continuous everywhere. If I take two functions that are continuous at c and I multiply them, the result is also continuous at c. So if I have x cubed and cosine x, we know that those are continuous everywhere. Then that means x cubed cosine x is also continuous on its domain. Similarly for the quotient, if I take a quotient of two functions, as long as g of c does not equal to 0, right, because we can't have 0 in the denominator, so assuming that that's not true, assuming that that's true, we can take the quotient and say that if the two functions are continuous at c, then the quotient must be continuous in its domain. So for example, if we know square root of x and cosine x are continuous everywhere, including at x equals 0 or whatever number, they're continuous everywhere, let's say x equals c, then the quotient must also be continuous in its domain at x equals c, okay? Which includes x equals c. It's what I was trying to say. So that domain would also include x equals c, and it's continuous there. Okay, so all right. So again, looking at that example, we know. Remember that I want to stress the fact that it's continuous in its domain. We know that, for example, it may not be continuous everywhere, but we know that it's continuous in its domain. That's what we want to focus on. It's that if the two functions are continuous in their domains, right, then the resulting function, the resulting quotient, would also be continuous in its domain. All right, so if g is continuous at c and f is continuous at g of c, then the composite function must also be continuous at c. So this is theorem 4.3. Composition. So if I have, for example, we're going to look at an example of this, but if I had, so let's say f of x is equal to x squared plus 1, right, for example, and I know that g of x is equal to the square root of x, and let's say that we know that x squared plus 1 is continuous at x equals 5. We know it's continuous at x equals 5. In fact, it's continuous everywhere, right? But let's just say we know it's continuous at x equals 5. And this is also continuous at x equals 5, right? Because square root of 5. There's no discontinuities there for x equals 5. Then f of g of x, which remember g of x is square root of x. So if I plug in square root of x, g of x is the square root of x. But if I plug that into f, that means I got to plug this into this. So I get square root of x squared plus 1. That's equal to x plus 1. That must also be continuous at x equals 5. That's what the theorem is saying. So in other words, so let's look at an example of that. So describe the interval on which each function is continuous. Now these are composite functions because here we have cosine of x, and we have the function f of x equals cosine of x, but we also have the function g of x equals 1 over x. So if I do this composition, I can write it as f of g of x, which is cosine of 1 over x, right? So there's two functions that compose it, basically, is what I'm trying to say. We can use the theorem 4.3 for this, okay? So for composition. So f of x is cosine of 1 over x. We know that that's continuous everywhere except for x equals 0. And this is how the graph looks like. That's the oscillating function. So it has the oscillating behavior here at x equals 0. But we know that the limit as x approaches 0 of f of x does not exist because of this oscillating behavior, similar to when we did for sine of 1 over x. So because the limit does not exist, and it's not continuous at x equals 0, then we can say that g of x is, so from theorem 4.3, we can say g of x is this portion, the 1 over x part. G of x equals 1 over x. We know that that's not continuous, so not at x equals 0. It's not continuous at x equals 0 because, it's going to lead to an asymptote there, infinite discontinuity. And therefore, because that's true, because that's discontinuous, that means that the composite function must also not be continuous at x equals 0. Okay, so it's something to keep in mind. This should actually say cosine of 1 over x, not sine. So I apologize for that. I just say cosine of 1 over x. All right, so basically we're saying that it's not continuous at 0 because of that behavior, and therefore it's continuous from negative infinity up until 0. We won't include 0, and then from 0 to infinity. All right, so for g of x, we need to see whether it's continuous at x equals 0, because we know that if we plug in 0 into here, that leads to issues, right? So clearly we know that it's not going to be continuous because of if I plug in 0 here, that's going to lead to division by 0, so that's going to lead to issues. However, is it going to be an infinite discontinuity or a removable discontinuity? We're going to find out now. So we know that sine of 1 over x has to be between -1 and 1, because remember, the sine function is always between -1 and 1, right? If you're to graph it. So that's always the case. So that means this has to be between -1 and 1 for any value of x. So then if I multiply this by x on all three sides, or absolute value of x, right? On all three sides, then I get this inequality here. And notice I don't have to put the absolute value here because it doesn't really matter as long as we know that that's going to be between these two anyways, okay? So we multiply by absolute value x and we get this inequality. So that means this has to be between those two x's, right? Negative x and positive x, absolute value. And then by the squeeze theorem, we could take the limit as x approaches 0 from all three of these. And then if I do that, well, then I know that if I do the limit, if I do a direct substitution here, I get 0, right? So it's equal to 0 on both sides. So then by the squeeze theorem, we know that because this is squeezed between these two numbers, well, the same number, that means the limit must also be equal to 0. So there actually is a limit here. So that means that it's not an infinite discontinuity, but there is a hole there. That's telling us that g of 0 is not defined, but there is a limit. So because we can't divide by 0, so we know we cannot put 0 here because that's going to lead to issues. However, the limit does exist, so that means that there's a hole. Okay, so we have a removable discontinuity. So the function is, we know it's not continuous at 0, so the answer is going to be the same. However, there's a little more nuance to it. Instead of it being infinite, it's just a hole here. Okay, so really interesting behavior. Just so if I were to graph, for example, just sine of 1 over x, so if I were to do sine of 1 over x, well, then that graph is going to look something like that, right? At 0, it's going to have that oscillating behavior, right? Right here at 0, so oscillation. So that's an oscillating discontinuity. So that's an issue there. However, it does oscillate here. However, there's actually a hole at 0, so it's actually removable here. Whereas this one is non-removable. This one is actually removable just by multiplying by x, interestingly enough. And we proved that using the squeeze theorem. All right, so at the end of the day, it's not continuous at 0, but it's continuous everywhere else. All right, so let's put a note on this. So the note on the part B, what we just did. If I wrote the function instead as this, a piecewise function, where it's the same exact function here, but this time we define 0, it to be equal to 0 when x is equal to 0, then now the issue with the hole has been removed. So if this were the case, the function would be continuous everywhere. And that's because now this thing that used to be a hole is now filled because of this part. So this is where we were saying it's removable, because if I redefine the function, it would fill in the gap and therefore make it continuous. So keep that in mind. All right, so let's look at another theorem known as the intermediate value theorem. So this theorem states that if f is continuous on the closed interval a, b, such that f of a does not equal to f of b, and k is a number in the interval f of a and f of b, then there is at least one number c such in the interval ab such that f of c equals k. So we're going to explain what this means. So in other words, assuming that the function is continuous, right, on that interval, if x takes on all values between a and b, then f of x must take on all values between f of a and f of b, including the value k, where k is between a and b. So let's look at a picture here, right? So we know that this function here is continuous. So let's put these here. We know that this function is continuous on the interval ab, right? So it's smooth and continuous, right? So it's continuous there. And because it's continuous there, and we know that f of a does not equal to f of b, right? They're completely different numbers. Then there must be a value c in between a and b, such that if I were to evaluate that function at c, it would give me a number, call it k, that is between f of a and f of b. That's exactly what we're saying. So basically, if it's continuous, we do have a number that exists between this interval that is between f of a and f of b. That's basically what it's saying. So let's take a look at that in an example. So we're going to use the IVT, the intermediate value theorem, to show that this polynomial has a 0 in the interval 0, 1. And then part B, we're going to approximate it. But let's focus on part A first. Note that this is a polynomial, so it's continuous everywhere. So it's continuous from negative infinity to positive infinity. So therefore, it must be continuous on 0, 1 as well, right? Therefore. So that issue is satisfied. That condition is satisfied. Remember, it has to be continuous for the IVT to be used. Using the IVT, we want to show that there is a value c in this interval such that f of c is 0. And we want it to be 0 because we need it to be 0 in the interval, right? We need to have a 0. So k is 0. So first off, let's go ahead and evaluate f of a and then f of b. Okay, so f of a, this is the f of a part. So f of 0 is negative 1. If I plug in 0 into this function, 0 into this function. And then this is for f of b. Oops, wrong one. I meant to put it here. So this is for f of b. So if I plug in 1, we get the value 1. So since k, which k is 0, since 0 is between -1 and 1, 0 is between these two numbers, that means that there is a value c there is a value c in this interval such that f is 0 in that interval. Okay. So let's look at so we basically showed that because these two numbers, because 0 is between those two numbers, that means that there is a 0 that exists, is basically what we're saying. And we need to figure out where it is. So that's what we're going to do in part B. Okay, so in part B, we know it exists. We want to figure out where it is. Okay, so x equals question mark. We want to figure out what x has to be equal to in order for this function. So we know that this function might look like this, and we know that it's continuous from 0 to 1. And so we know it's continuous, and we know that there's a 0 somewhere, but we don't know where, right? That's what we just proved. Okay, so let's go ahead and do this. So we're going to approximate the 0 by the bisection method. Okay, this method is very tedious, but it's a good way to kind of illustrate how to do this. So since the 0 must lie between 0 and 1, we'll cut the interval in half or bisect it. Bisect means to cut in half, right? So the 0 must either lie in 0 and 1/2 or 1/2 and 1. Basically, we took this interval, which was 0 and 1, and we cut it in half. So basically, we have 0 and 1/2, and then 1/2 and 1. Basically, that's what we did. We bisected it into half. And we can use this formula, right, to bisect it. Just take the average of a and b. A plus b divided by 2. All right, so we're going to do those two intervals. That's what we have. So we have the 0 to 0.5 interval, and then the 0.5 to 1. We're going to plug it in. F of 0, f of 0.5, f of 1. And we get those values. So now I want you to note that when we plug those in, the 0 must be in the interval 0.5 to 1. It must be in this interval because this 0 is between that negative number and that positive number. And that tells us that we need to just get rid of this. We don't care about that. We want to look at these two numbers, this interval, because the 0 must be between those two. All right, so therefore we're going to look at this interval and we're going to break it in half into these two intervals. Okay, so again, I crossed out that first value because we don't care about that, and I divided this into these two intervals because I cut it in half again. And now we already know what these numbers are, so let's plug in 0.75. If we do that, if we plug in 0.75, we get this value right here. Now notice that the 0 must be in this interval right here because 0 is, so we can get rid of this, because 0 is between this negative number and this positive number. All right, and we're going to cut this in half into these two intervals. And so we're getting rid of this, like we said earlier, and then we're going to include the 0.625. Now we're going to plug in 0.625 into the function. We're plugging it into this function, of course, and we get this value. And notice that the 0 must be in this interval because 0 is between negative number and a positive number. And then, therefore, we're going to split this in half. And we're going to keep doing this until we get it. So now we got 0.6875. We're going to plug that into the function and see what we get. We get 0.012. Notice that the interval, that 0 is between these two. So we can get rid of this and just focus on this interval right here. So 0 must be in that interval. So we're going to bisect that interval. And then we're going to plug in for this number into the function and get negative 0.6061. So 0 is between this negative number and this positive number. So therefore, we have to look at this interval. So we'll get rid of the first interval, look at the second interval. We're going to bisect this one more time. And if we do that, and we're going to plug this number in to there, we get negative 0.025. So it's, again, zeros between this and this. So we're getting really close at this point. Since we're really close to narrowing down the interval so that we get almost exactly 0, we can confidently say that the 0 must be between these two. And so we can say that the 0 is approximately 0.67, 0.68. So we're going to say it's around 0.68 and call it. Okay, we can of course keep bisecting it and get a more accurate answer, but we're close enough where we can actually tell. So this is the graph. This is how the graph looks like, and notice that this is the 0 right here. This is where it crosses the x-axis, and notice that the value of c, which is the 0, is 0.682. That's really close to what we just said. All right. Okay, so that is it for the lesson. Here are some review exercises. You can pause the video and write down these exercises, work on them, and then we're going to review them. So this is part 1 of the review. So there's 7 questions here. So here's part 2 if you want to pause the video and work on the questions to make sure you understand the content. And then we'll review. All right, so looking at the first question, hopefully you paused the video and tried the question before looking at the solution, just to kind of check to see if you get it. So here we're going to discuss the continuity of this function at c equals -3, right? So that's the function that we're trying to do. So clearly we can see that it's not continuous at c equals -3 based on the graphic here. However, we're going to discuss it. So we're gonna using the properties and stuff, we'll explain why. So if I were to use the one-sided limit as I approach -3 from the left side, then that's going to give me a value of 3, right? If I do the limit as x approaches -3 from the right side, that's also going to give me a value of 3, right, on here. So the limit exists. We know that the limit as x approaches -3 of f of x it exists. We know it exists, and it is equal to 3. So remember that continuity at a point, you have to satisfy 3 properties. The limit must exist, the function must be defined, and the limit must equal to the function. Well, we know that the function at 3 is defined. F of 3 is defined, or -3. F of -3 is defined, and it's actually equal to 4, right? So f of -3 is 4, because that's where this filled-in portion is at 4. Okay, so we set those 2 properties are satisfied. However, the third property is not satisfied. In other words, the limit as x approaches -3 of f of x does not equal to f of -3. And therefore, we're going to say it's not continuous. So therefore, it's not continuous at x equals -3. And in fact, it's removable because we know that the limit exists, right? And the one-sided limit exists. We know that the limit exists, but it doesn't agree with the value of the function at that point, at that value. So we're going to say there's a hole. It's a removable discontinuity. And I say it's removable because we could define this to be 3. If this were equal to 3, then that would resolve the issue of the continuity, right? So that's why we're saying that that's removable, because we could redefine this to make it work. All right, so that's the reason why I'm saying that. All right, so number 2. So a similar type of problem here. We have a jump discontinuity, however. So for this jump, so I guess what we should say is that this could be removable, but right now, because it's defined at 4, it's technically not removable unless you omit it entirely and then redefine it. So I just want to clarify that again. Now this is a jump discontinuity, right? We can see from the graph, and let's see. So we know it's not continuous. But let's go ahead and look at the one-sided limits. Now, if we were to do the one-sided limits, you're going to get different values. So if I approach -1 this is -1. If I approach that from the left side, meaning I have to traverse this portion of the graph, well, it's gonna approach this value of 2. If I approach -1 from the right, then it's got to traverse this portion of the graph, and that's going to approach this value here, which is 0. Okay, there's a value of 0 right here. So the limit of f of x as x approaches -1 from the left is equal to 2. The limit as x approaches -1 from the right of f of x is equal to 0. We see that these two one-sided limits do not agree, right? So we're going to say, so since they do not agree, so we're going to say this limit here does not equal to this limit here. This is from the left, this is from the right. Therefore, the limit does not exist. Okay, so that limit does not exist. If they don't agree, the limit doesn't exist, and automatically it's disqualified. So so it's not continuous. So it's not continuous at x equals -1. And in fact, there's a jump discontinuity, and you could tell because the one-sided limits do not agree, right? So I guess for the previous one, I should really say that there's a hole there, right? So in fact, I'm going to go back here. I'm just going to say this could be removable, but I'm just going to, just to be more accurate here, I'm going to say there's a hole discontinuity. There's a hole there, which usually it's removable if you redefine it, but I'm just going to redefine it as hole just to be unambiguous. So we have, and this is a jump discontinuity. You can tell because it's the one-sided limits do not agree. So it's jumping around between two different values. All right. Find the limit if it exists for number 3. We just want to determine if it exists. And then if it exists, what is the value? So if I look at this, we have an absolute value here, right? So remember that the absolute value function is defined to be a piecewise function where it's equal to negative x if x is less than 0, or positive x if x is greater than or equal to 0. Okay, so that's essentially what it's defined, right? So in other words, if we were to do the absolute value of x minus 10, so I'm going to change this to x minus 10 instead, which is what we have, then this is equal to, let me erase this and replace it with x minus 10. In fact, let me just erase the whole thing and rewrite it. So now in terms of absolute value of x minus 10, this is defined to be the opposite of the quantity x minus 10 if x is less than negative 10 or positive 10. Basically, whatever makes this 0, that's the turning point, right? That's the turning point that we're looking for. And then it's equal to the quantity x minus 10, in other words, the original quantity, if x is greater than or equal to 10. Okay, so in that case, if we can, since we're doing 10 from the right side, which is this quantity right here, this is from the right. So since we're doing this from the right side, we're going to be using this portion right here. So we can replace the absolute value of x minus 10 with just x minus 10. So we're going to say that this is equal to the limit as x approaches 10 from the right side of just regular x minus 10. But notice that these cancel, and that leaves me with 1. And the limit as x approaches 10 of 1 is just 1. Okay, so that's the limit. So the limit is 1. And let's go ahead and look at a sub-example. What happens if I were to do this from the left side? So if I were to do this from the left side, then that means we're looking at this inequality right here, right? When x is less than 10. So this here is from the left. In that case, I would replace the absolute value of x minus 10 with this here, and I would write negative x minus 10 over x minus 10. And then notice that these will cancel out, leaving me with negative 1. So I get the limit as x approaches 10 from the left of negative 1, which is just negative 1. Okay? So we know that the two one-sided limits do not agree. So we know that the overall limit does not exist, but the one-sided limit does. Okay? So just a side note. A side example, if you will. All right, so find the limit here. This is from the left side. So as x approaches negative 3 from the left. So remember, when you do one-sided limits, you could do a direct substitution. So we're going to try plugging it in directly first and see if that works. All right, so if I do a direct substitution, I notice I get negative 3 over square root of negative 3 squared minus 9. So I get negative 3 over square root of 9 minus 9, which is negative 3 over 0. Now, this is not an indeterminate form because it's not 0 out of 0. So it's not like you cannot, you cannot cancel things out in order to get a value here, right? So when you have division by 0, as long as the numerator is not 0, this indicates that we have a vertical asymptote. Okay, so we have an asymptote at x equals negative 3. And so because we have an asymptote, that means that this is an infinite discontinuity. Okay, so so basically we have something where, as x approaches negative 3, we have an asymptote there where it's, maybe something like this, right? Where it just jumps. So that's an infinite discontinuity. We have an asymptote there. So the limit does not exist. When you see division by 0 like this, the limit automatically does not exist. So this is D and E. Does not exist. All right, so discuss the continuity of each function. All right, so we have a piecewise function. We want to determine if it's continuous. So again, we could graph it, or we could just use the calculus to help us do this, right? So we want to figure out, obviously, if it's continuous at 1, right? So let's go ahead and say, okay, what is f of 1? Well, f of 1 is, so when x is equal to 1, we have to use this portion of the function because that's where it has the bar, right, equal to. So x is less than or equal to 1. Well, then if we plug in 1 into here, then that's just going to be 1, right? So f of 1 is 1. So this is defined. So check, it's defined. So that looks good so far. And then we're going to see if the limit is defined. So in order to do the limit, we need to do the one-sided limits to see if they agree. So let's do the limit from the left side. The limit from the left side means we have to use this side because this is from the left side and this is the right side. Okay, so let's use the limit from the left side. We're using that function in there. So basically we're saying that we're doing the limit as x approaches 1 from the left of x. The function is now x that we're using. Well, if I plug in 1 into there directly, I just get 1. Okay, now let's do the limit as x approaches 1 from the right side. Well, because I'm doing the right side, I'm doing this function right here. So I'm just going to redefine that as 1 minus x. Well, if I plug this into there, I get 1 minus 1, which is 0. So we clearly see that the limits do not agree. So the limit as x approaches 1 from the left does not equal to the limit as x approaches 1 on the right. And in fact, I'm actually not going to, so we can just leave it like that. I don't want you to confuse this, the whole x and 1 minus x thing. I just want you to know that if it's from the right side, you plug it into this. If it's on the left side, you plug it into that function. That's really what I want to mention. But the limits do not agree. You get 1 and 0 for the other one. And therefore, the limit as x approaches 1 of f of x, the two-sided limit, does not exist. So that's telling us that we have a jump discontinuity. All right, so discuss the continuity. So it's not continuous at x equals 1. All right, so let's look at the next one. We have, so discuss the continuity of this guy. So first off, if you look at the function, you might notice that if I plug in x equals 0, that's going to lead to some issues potentially, right? So x equals 0 question mark. Let's plug in. Let's see what we get if we plug in 0. So we get 0 over 0. Okay, so we get something that is an indeterminate form. Also, so basically what we want to do is we want to factor this bottom part out. So let me do that. So let's factor it down over here. So if I factor the bottom part, I get x over x. I can factor out x from the denominator, and I get x times x minus 1. So clearly that means that if I plug in x equals 0, that's going to be questionable. If I plug in x equals 1, that's also going to be questionable. So we also have x equals 1. That's also questionable, right? So let's also do x equals 1. So if I do f of 1, I get 1 out of 1 over 1 squared minus 1, which is 1 over 0. Okay, notice the difference between these two. On the top one, which is 0, I get an indeterminate form, which indicates that there might be a hole in there, and so there is a value when we do the limit. However, the function itself is undefined, right, at that point. So we have a hole at 0. However, for 1, we have an infinite discontinuity. So we have an asymptote here. Okay, so we have an asymptote. In fact, a vertical asymptote. So therefore, there's definitely a discontinuity there, an infinite discontinuity. There's a discontinuity at 0 as well, but it's going to be a hole. Okay. So we're gonna figure out. So we're just gonna say f of 0 is undefined. However, we're gonna see that the limit agrees. So there's actually a value associated to it. So we're gonna do that down here. Okay. So for x equals 0, let's do the limit as x approaches 0 of the function. But we know that if I factor it, I get x times x minus 1 on the denominator. That cancels out, leaving me with 1 over x minus 1. Then if I plug that in, doing a direct substitution, I get 1 over negative 1, which is negative 1. So the limit exists, which means that we have a hole. So we have a hole at x equals 0. And an infinite discontinuity at x equals 1. All right, so it kind of gives you an idea of how to analyze that. And this hole is a removable discontinuity. So I'm going to put this infinite discontinuity is non-removable. This hole is removable. Okay, so let's discuss the continuity of tangent pi x over 4. Okay, so remember that the tangent function tangent of 0 is 0, and then we know that it's not defined at pi over 2 and negative pi over 2. So when we graph the tangent, this is just one period of the tangent function, and of course it continues on forever into multiple periods, right? So like there's different copies of it, if you will, that are each shifted with a period of pi. But yeah, there's multiple iterations of the tangent, but this is just one of them. Let's just focus on the one. Basically, if this here is equal to pi over 2 or negative pi over 2 or any multiple of pi over 2, then basically, yeah, let's actually do that. So let's actually draw the other one. So this can also be pi. right? And so on. The next one's 3 pi over 2, and so on. So for every multiple of pi over 2, except for 0, for n being 0, okay? So what we can say is that for the tangent function, this is continuous everywhere except at x equals n times pi over 2, where n is a positive integer. Where n is a positive integer. Okay, so n has to be like, or where n is a, where n does not equal to 0. Sorry, let's just say that n does not equal to 0. So n could be a negative integer as well. So you could have negative pi over 2, negative pi, so on and so forth, right? Positive pi over 2, positive, 3 pi over 2, all that. We're just going to do this in terms of this function now. So if I look at this function, well, this has to be equal to n pi over 2, right? In order for it to be not continuous, right? So it's not continuous when this is equal to this, basically. Okay? So then if I do that, well, I mean, the pi's cancel. Let's multiply both sides by 4. So when x is equal to 4 divided by 2 is 2, right? So when x is equal to 2n, then this is not going to be continuous. Where, again, where n cannot be, where n cannot be 0, okay? So, so we have basically vertical asymptotes when x is equal to 2n. So we got infinite discontinuities at these values. Okay. All right, so I think we're in the part 2 questions. So discuss the continuity of the function over the given interval. So we have this function from -1 to 2. So we're looking at a closed interval now. So we're looking at continuity over closed intervals rather than just at points. So we need to determine if it's continuous on the open interval, and then we need to do the, of course, then we need to do the one-sided limits. Right? So first off, let's go ahead and factor this here. Factor this using the difference of squares. So this is the same thing as 1 over x plus 2 times x minus 2. So using the difference of squares, we can factor that. And so we can see that there are some troublesome points here. So it's not continuous at x equals -2 and x equals 2. Because if I plug in 2, that becomes 0. If I plug in -2, that becomes 0. And we cannot divide by 0, right? So we have infinite discontinuities at -2 ends 2. However, we can safely discard -2 because that is not in my interval that we're looking at. So we're going to ignore that for the time being, or we're just going to ignore it. However, x equals 2, it's not continuous in there. So therefore, because this is closed, it's not continuous at 2, so it's not continuous in that interval, okay? So we have an infinite discontinuity at x equals 2. So the function is not continuous over the interval -1, 2. So the function is continuous over this interval, but it's not continuous at this. So let me put a side note. So the function, so f of x is continuous on -1, 2, right? However, because the limit as x approaches 2 from the left side, now we're going to see whether this is closed or not, right? the limit as x approaches 2 from the left side, if I plug in 2 into there, I get 1 over 0, does not exist. So it's not continuous on the closed interval. So we're also going to say, we're also going to do this here, right here. So we're going to prove that this is closed at -1. It's not closed at -2, right? So it's not closed at 2. We're going to show that it's closed at -1. So we're going to do the limit as x approaches -1 from the right side. If I plug in -1 into there, then it works. I get 1 over -1 squared minus 4, which is -1/3. Okay, so that means it is closed at -1, but it's not closed at 2. So we're going to conclude that it's not continuous at -1, 2. Right? You could just say this top part, and because of that, we can say it's not continuous on that interval. However, I wanted just to be more explicit and show you that it is continuous. It is continuous from -1. It is continuous from negative on this open interval and on this open interval and on this mixed interval. Right? So it is continuous when -1 is inclusive, but the troublesome part is the 2. All right? So yeah, a little bit more explanation is necessary, but I wanted to include it nevertheless. So, all right, so use the intermediate value theorem to determine if the function has a 0 in the interval 0 to 1. Okay, so this is my A and this is my B. We want to plug in f of A and f of B. In this case, h of A, h of B. So h of A is h of 0. So we got 2 cosine of 0 minus 3 times 0. So cosine of 0 is 1. So we got 2 times 1 is 2. 3 times 0 is 0. So we have the value 2. H of B is equal to h of 1. So B is 1. So we're going to plug in 1. So 2 cosine of 1 minus 3 times 1. So 2 cosine of 1, that is a decimal. You need to do that on the calculator, okay? So because that's in radians, so it's going to be a decimal. So let's go ahead and do that on the calculator real quick. So the cosine, 2 times cosine of 1 minus 3. Okay, so if I plug it into the calculator, I get negative, and this is in radians, right? Not in degrees, this is radians. So negative 1.92 around there. Okay, so basically we have a negative number when we do this, right? So what that means, and we have a positive number here. And so we want to see if it has a 0. Well, by the intermediate value theorem, since 0 is between h of A, which is 2, let's put the negative number first. Since the number 0 is between negative 1.92, which is h of B, and 2, which is h of A, since it's between h of A and h of B, basically, then that indicates that there is a 0, okay? Since this is true, that means there exists a 0, which we'll call C, and C is in the interval 0, 1, such that f of C is equal to 0. Okay. All right, so basically what we're saying is that because we end up having a negative number here and a positive number here, and that means 0 is between those two numbers, that means that there exists a 0 in that interval 0, 1. Okay. All right, so that is the end of the lesson, guys. I hope you took something from this video and you learned something. As usual, I'll see you in the next one.